I'm not very good at equations, and I like sloppy presentations. So you may find this quite different from the previous presentation. So this is all I've written about how to compute cloud atmospheres. So it's pretty much a simple description, and so you're not going to find out here how to do it. You have to go look at the sources. So you start by making an LTE hydrostatic fluid. Build an LTE hydrostatic equilibrium model. You start by specifying the parameters, the effective temperature and the gravity and the abundances. Then you, since there are already thousands of models available, you take a starting model to guess what the temperature optimal depth relation is in the atmosphere. Then you compute the equation of state, the number densities for all the species. And using those number densities, you compute the lining continuum opacity. Then you compute the radiation field and the flux that the radiation field produces. If you're doing a late type star, you also have convection, so you have to compute convection and add that to the radiative flux, and you end up with the total flux. And that total flux is not going to be the correct flux for the star. So you have to have some method of temperature correcting, and you change the temperature at each depth, and then you keep iterating until you get constant flux all the way through the model. And at that point, you know what the convection is as a function of depth, and you know what the radiation field is as a function of depth. So this has been explained in the references we just heard about, the Houvini, the Mihalis. I wrote up one of my early versions of Atlas in SAO Special Report 309. You can find these on my website here. I'll skip this. You find it on my website. And there are also previous talks I gave in Fiesta on the subject, and where I went into detail, and it's all written down. There's a paper on Atlas 12, Cynthia, Atlas 9, and WIP 9. There are papers on numerical limits of the programs. There are papers on including all the lines. There's one on all the numerical tricks for making the programs run fast. And there's one on high resolution, high signal to noise atlases, which you need to test your calculations. Now, I gather that most of you are just starting out. So what I suggest is that you just go get the models from the web. You can go to my website. You can go to Fiorella Castelli's website in Trieste. There are thousands of models, or tens of thousands of models that vary with various effective temperatures, gravities, abundances, alpha process enhancements. And you can, there's so many that you can just interpolate any model you want. If you want to get into the real nitty-gritty, you can get the Linux versions and the explanations for all the programs from her. Now, there's been a new development. Some people have their own mini supercomputers with thousands of nodes, and I've heard of people who think nothing of computing 1 million models at once. They vary the metal abundance, they vary the alpha elements, they vary the C to O ratios, so you can just go to them and get the models you want directly. Now, once you know how to do that, and you're not worrying about it anymore, then you can go in and learn all the details of how to compute them yourself. So I'm only going to talk about some details that are not part of these write-ups and not part of the papers, but are things that you should know about so you don't have the false impression that everything is easy and like it is in textbooks. There actually are problems that you should worry about, because if something goes wrong, you should know or suspect that it could be some of these problems people haven't told you about. But I'm telling you. So there are problems with convection, microturbulent velocity, equation of state, and rotation. And then this afternoon, I will tell you about various treatments of opacity. You can have fully resolved spectra where you have all the details, and those are produced with program Cynthia. You have sampled spectra, and that's with program Atlas 12. You can have low resolution distribution functions using DF Cynthia and Atlas 9. So I'll come back to that later. So I'm using the term Cynthia for a whole suite of programs for computing spectra. And Cynthia.4 is just one of those in the suite. The first program that computes the equation of state is called XNFPEL SYN, and the X stands for abundance, N is number density, F is ionization fraction, P is partition function, and L is electrons. So it does calculates all those variables. Then, once you have those tabulated, Cynthia reads them in and computes the line opacity for the whole spectrum. Once you have the whole line opacity computed, Spectra reads it reads in the number densities, it computes the continuum opacity and the radiation field. So you end up having the spectrum computed. You have to add macro turbulent velocity if there are large-scale motions in the atmosphere. And then, since all stars are rotating, you have to add rotational broadening. And then, in order to observe a star, the light has to go through a spectrograph, which produces instrumental broadening, so you have to add that. So at the end, you end up with a spectrum computed, and you plot it up with your observed spectrum and make a comparison. So the most important part is making that comparison of a computed spectrum that's been degraded to the observational accuracy compared to the observed spectrum. And what you end up doing is finding that they don't match. And you have to do it all over again, which improves the errors you find, and you do it over again and iterate until you get a final spectrum that looks like the real thing. Well, here's some more of the real thing. When I was raised, stars used to be spheres and had constant effective temperature and constant gravity, but actually stars are rotating. Young ones are rotating very fast. This is Altair. It's rotating at 273 kilometers per second. It's oblate because the centrifugal forces at the equator is pushing out material, so the density is lower there, and the surface gravity at the equator along here is only 3.85 log g. At the pole, which is down here, the gravity is 4.27. And the projected rotation velocity, which you see along the edges here, is 245 kilometers a second. Because the density is so much lower at the equator, the temperature drops to 6890 degrees, but at the pole, it's 8740. This color map is very deceiving because this is the brightest spot and this is the coolest. So I should have it reversed. Now there's another favorite star, Vega, that I've worked on for my whole life. And when I worked on it, it looked like this. It was a sphere with effective temperature of 9,400 degrees, log G of 3.95, and V sin I was 23 kilometers a second. So it was rotating like this, and, going in 23 kilometers a second there, and coming out 23 here. And it gave perfect match to the observed energy distribution and Balmer lines, which I'll show you in a minute. However, lately, you and Peterson and Zagarello have used interferometry and determined better parameters with higher quality, will have better, higher quality data, and it's also rotating at 236 kilometers a second. And what we find out is that Vega actually looks like this if you looked at it from the equator. But since we're looking at it pole on at a 5-degree inclination, it looks spherical. And the temperature at the pole is 10,059 degrees. At the equator is right here, it's 8152. The gravity is factor 2 higher at the pole than at the equator. So this is the old-fashioned Vega, and the dots are the spectrophotometry, which is claimed to have a systematic accuracy of 2% in the visible, 3% in the ultraviolet. And you notice there are nice, relatively smooth lines formed by the dots. Now, since the error could be systematic, it means that this whole section could go up and down 3%. But it matched, so we were happy. And if you try to match the Balmer profiles with observations by Peterson, you find very good match except near the line centers. So we have a problem here that we can match the observations very well using the wrong physics. So why is that? Well, we have to think about the observational pipeline. Nature has this way of making a pipeline, just like they do at telescopes. So it takes this rotating star and sends the light to us. The light passes through circumstellar material. Turns out there actually is circumstellar material around Vega, but it's a debris that's far out from the line, from the center of the star, and it doesn't matter to what we're talking about, but you can see it in the scattered light in the far infrared. And then there's interstellar reddening, and I don't actually remember the number for Vega, but it's tiny. But you can't ignore it when you start worrying about details at the percent level. Then there are interstellar lines, and nobody sees those because no one ever takes a high-resolution spectrum of Vega because it's a fast rotator, or considering 23 kilometers fast rotation. But if you did, if you took a spectrum with resolution 100,000, you would see interstellar lines. They're diffuse bands, and you probably never see those. And then the light gets to the surface of the atmosphere, where there's solaric air glow, so lines of NO, OH, sodium are emitting and are added onto the spectrum. Then it goes through the atmosphere, and if you're in the southwest of the United States or around any observatory that was built a long time ago, it's surrounded by retirement communities that have a lot of sodium lights. So you get scattered light into your spectrum. In passing through the atmosphere, you see lines or broad bands of ozone and O2 dimer. Then you see the caloric lines, water and O2. There are aerosols, dust that absorbs. Then you get to the telescope and you have reflections on the silver surfaces of the telescope, and dust gets on those surfaces. Then you have instrumental transmissions, scattered light, your detector sensitivity, cosmic rays, and the instrumental profile. And at the end of all that pipeline, you have an observed spectrum. So what we want to do is model the observed pipeline with a computational pipeline that does the same thing, except we have to do a lot of work up top there to get a rotating star giving off the radiation. So we have to compute grids of models and grids of spectra and then integrate over them to get the spectrum of the star. And you can actually compute all of this process. You can get the information from the engineers who do this telescope and what all of these are. And you can get the information for these other things. But I haven't done that because most of them don't matter, in fact. But sometimes they do. And especially if you're working at high resolution or high signal to noise. So for each step in the pipeline, you need a program or a group of programs. And so I've written programs that compute the model atmospheres, Atlas 9 or 12, do the spectra, do the macroturbulent broadening, and another program for doing the rotation. And then I haven't bothered with the any of the interstellar stuff because they actually haven't mattered. When I get down to Earth's atmosphere, I start worrying again because I can see the stuff in my spectra. I don't see the air glow because I'm looking at bright stars that are much brighter than the air glow or the anthropogenic light. But I see the ozone, I see O2 dimer, I see O2 lines, I see water lines. So I've programmed those. And I assume that the people who operating the telescope and their reduction pipeline work, and all I have to worry about is putting in instrumental broadening at the end. So then I put all this together and plot it up with the observed spectrum. So now I'm going back to the 4 problems I was going to talk about: convection, microturbulence, creation of state, and rotation. So one of the things people seem to skip over, and I especially skip over, is that my programs only compute photospheres, but that real stars, especially late type stars, all have chromospheres, which means you're starting off with a fundamental disadvantage of leaving out a lot of the physics. So this is an empirical model from Fontainebleau, Averett, Loser, and it's the black line here. The photosphere falls down and tau equals 0 here. The temperature is around 5,800 degrees. It goes up to tau equals 100, tau 10 to the minus 6. And the model photospheres I compute continue downward monotonically this way. But the real temperature distribution derived empirically stops at temperature minimum and then goes back up. And there's convection and microturbulence of about 2 kilometers a second. This is 1 kilometer, 2, 3. And as the convection dies out, the microturbulence dies out. But the atmosphere has magnetic fields. And as the convective elements rise up to this point, they start knocking against field lines and produce waves that heat up the chromosphere and generate additional microturbulent velocity that you can see in the chromospheric lines. They get much broader. And so you have a microturbulence that goes to 0 from the photosphere, and then another microturbulence that starts at 0 and climbs up. Just one important thing is that the star is born with strong magnetic fields and a very active chromosphere. It's much brighter than you would in the ultraviolet when it's young than as it ages and the field dies down. So that means that the chromosphere is not an equilibrium structure, and in order to model it, you have to specify how much energy is being lost. And one can estimate where it starts, where the temperature minimum is, simply by taking 0.76 times the effective temperature. And that'll give you approximately this value. And you know that the photosphere above that is reasonably accurate, and below that it starts getting worse. So for my whole life, I wanted someone to figure out how to compute model chromospheres and tack them on to my model photospheres, but no one's ever done it. So I hope one of you people will become interested. So this next, from the microturbulent point of view in convection, it turns out that the microturbulent velocity, when it derives empirically, is the same as the convective velocity. This is just an empirical fact. So the conclusion I draw from that is that the microturbulent is convection, or directly proportional to convection. And that, in fact, is what you see in three-dimensional sophisticated models. So I did an experiment. I took a whole bit of models with varying effective temperature from 3,500 degrees to 8,500 degrees. And I plotted the convective velocity, maximum convective velocity in the atmosphere. So this is 0 kilometers, 20 kilometers at the top. So in an M dwarf at 3,500 degrees, the maximum convective velocity is 1/4 of a kilometer per second. And in an M supergiant, it's more than 4 kilometers a second. If you go to a 5,500 degree supergiant, it gets up to 20 kilometers per second.
I'm sorry?
Yes?
What do you mean by maximum convective velocity? What is the maximum?
In the atmosphere. So in the plots I showed previously, the optical definitely went down to 100. So in that range. Because it doesn't matter what, you can't see at the surface what's happening below optical depth 100. And then, however, just because the convective velocity is small, just because you have a convective velocity doesn't mean that is relevant unless the convection is actually carrying a lot of energy. Because it could be only a small fraction of the mass is convective. So what this plot shows you is the fraction of the energy carried by convection. And you see that in most stars, it's more than 95%. And then as you get higher and higher, the lower gravity stars become radiative, and only on the main sequence is convection strong. So I estimate that microturbulent velocity, the convection velocity that would appear as microturbulent velocity, is some number of this product of this. It's an ad hoc guess. So that reduces the strength where the models become radiative. Now, this was a grid of models with constant microturbulent velocity of 2 kilometers a second. But what we see is that the convective velocity varies. It increases as you go to higher temperatures. It increases as you go to lower gravities. And microturbulent velocity must do the same thing. But microturbulent, if you look at the grids of models in the literature, on the web, that anyone computes, they have constant microturbulent velocity. It's only 3D models where the microturbulent velocity comes from the convective motions automatically, where you're including depth-dependent microturbulent velocity. So I modified my programs to include a depth-dependent microturbulent velocity that, like this, it varies with depth like this in the sun, but is scaled to the numbers we saw on the graph. And that seems to work. So it means that microturbulent velocity is a much more complicated parameter than people have assumed, and it's just not one number you're going to get. Or if it is a number, it tells you the scale, but the actual values vary with depth and vary with effective temperature and gravity. Then there's the equation of state. My programs were written before all of you were born, and it turns out that physical numbers have a short lifetime. Every time you go to the lab and do something better, the numbers change. So the wavelengths of lines, the energy levels, physical constants, even the speed of light is changed. And so the program has to be constantly updated. But if there hasn't been any new laboratory data, it hasn't been updated, and it can still be way out of date, but not obsolete because it's not been replaced. So if you're worrying about less abundant elements that are not likely to have been well studied, you have to check yourself that the partition functions are good, that the ionization potentials are good, and the equilibrium constants for molecules are good, or you might end up having some systematic errors in your abundance results. And I'm now computing new line data, and I'm recomputing partition functions for all the elements, but it's going to be a while before that gets incorporated. Okay. Then we're going to talk about rotation. So I showed you these oblate stars. You can, well, the theory of gravity darkening is not well known. So one of the problems is if the star can rotate rapidly, there can be differential rotation and meridional circulation. So you can't, and people haven't worked out the theory completely. So one uses a simplified gravity darkening model that specifies the effective temperature and gravity as a function of coordinate on the star, and determines the projected velocity at each point. And then, as long as you're not doing a supergiant, but are doing a relatively small star where the atmosphere is plane parallel, you can just interpolate in a grid of models in spectra and just determine at each coordinate on the star a model that matches that point. So essentially, you're interpolating both in effective temperature, gravity, angles, and velocity. And it's a big interpolation problem, but not a big problem in physics. But it's only been done for a few stars. So you put a grid over the star. This represents a grid in it, and it came out with a funny pattern, which actually is visible. Grids I actually use have about 200 points in the stellar radius, so they're 40,000 by 40. They're 400 by 400. They're more than 100,000 points spread over the surface of the star. And for Vega, we have the rotation of plus 23 kilometers, minus 23, and then the V sin I varies to 0 at the center. And you can integrate over this surface and get the rotation unit and get a rotated spectrum. And you can do the same thing with many more degrees of variation, because you have the gravity varying from 366 to 402, the temperature varying, and the velocities vary. So if the work you're going to be doing and the work I do, I use the simplified model. But if you have really good data, you can try more complicated ones. So this is a way of introducing a new explanation for why your program doesn't work. Okay, so I'm just going to run through the pipelines. So there's atmospheric transmission, so OH, NO, and other radicals, and they've been tabulated by Osterbrock, so you can have a line list and know where to look for something. If you see a bump, you can check to see whether it's an emission line. But I haven't done it. I haven't programmed that. There's a catalog of emission lines that are anthropogenic by Slanger et al. And I haven't programmed that. But if you have spare time, you can program it. Then the circumstellar material, you can go to disk people and have them model the various disks or shells or outflows. But hopefully you stick to stars that don't have any of that. I have a program for reddening SEDs using standard reddening laws, and that could also be used for reddening spectra. If you look for the diffuse bands, there's a catalog by Kuruc, and that could be programmed up. Most of the local stars that are bright, and it isn't going to matter. Then there are the interstellar lines. Those are lines that are resonance lines from low energy levels, say less than 300 wave numbers. So if you just go through my line list and pick out all the lines that are strong from low energy levels and look for radial velocity offsets from strong lines in the stellar spectrum, you should see the lines at the same radial velocities. You can identify them that way, and you can write a program to calculate them. So I have programmed the atmospheric transmission. So this is a list, and there are pictures that come after this. So there's a program called Cynthia, which computes the opacity of the ozone, O2 dimer, and all the telluric lines. Then there's this program, Spectra, that takes those data and does something complicated. When you take a spectrum, it's moving across the sky, the star is moving across the sky while you're observing, and the air mass changes. And it's nonlinear, so what you have to do is divide up the observation into small pieces and track the air mass as you go, and then integrate, find out what the actual transmission spectrum is. In other words, you sum up a large number of 5-minute integrations to get the effective transmission. And then the program transmit that multiplies that times the stellar spectrum. Turns out there are atmospheric models with Earth's atmosphere for different latitudes, different seasons, different amounts of various variables. And I never learned about those when I was in school. They didn't teach us about the atmospheric transmission. Then I have programs for computing ozone and O2 dimer, and mainly I have a high train line list from Larry Rothman, who used to work for the Air Force and now works for the Smithsonian Observatory. And his line list used to be really terrible and invisible because the Air Force was only interested in the infrared, because they were looking for laser transmission with weapons. But now it's been improved, and it has data running all the way through the visible, and it also has lots of lists of pollutants in the atmosphere. So here's some model for the terrestrial atmosphere. It's mid-latitude, July atmosphere. So this is the sort of thing you could use at Kitt Peak or someplace above the tropics, and it shows the temperature as a function of every kilometer, and pressure and number density. And then it has a table of average water and average ozone. And if you try to use this model with those numbers, it's always wrong. So you have to scale the water and scale the ozone to match your spectrum. Or better yet, you get somebody nearby at an airport to send up a radio sign and you actually measure the water and then use those numbers. So this is what the ozone looks like. This part is straight scale. This is times 10. If you look at your spectra of early type stars in the ultraviolet, you can actually see these bands. This is factor 10 times scale. This is the ozone Chapuis bands. They're formed not high up in the stratosphere, but low, relatively low in the atmosphere. And unfortunately, this is where H alpha is. And so you have this feature crossing H alpha at an angle, and so it means that you can't use the wings of H alpha very effectively. These are the O2 dimer bands. You can see they're about 300 angstroms wide. You find a dip in your spectrum, it could be caused by one of these. So this is all, fortunately these things are all computable. And the product of the two gives you this. So this is actually what you see around H alpha. So what I do is I compute these and remove them from my observed spectrum. And then I end up with a flat spectrum. And these are the Hytran lines. There are water lines here in the infrared, which make the infrared pretty useless. But the O2 bands, the A band, the B band, and little weak ones. And then these are at 10 times scale. You see water all the way into the ultraviolet. So this can be computed accurately sometimes. So you then plot the computed spectra with the observed spectra. And this is a cheat since it's actually a space telescope spectrum, but it's one that has lots of pretty colors, so I like using it no matter what. Up at the top, we've labeled every line that's significant. So you can try to work out the blends. And then I've computed the spectrum twice. The blue line is with 0 rotation velocity, and the red line is the actual 16 kilometers per second spectrum, computed spectrum for Sirius. And the black line is the observed spectrum for Sirius. So the purpose of the 0 rotation spectrum is to help you figure out when the lines are blended. And in fact, no, they're always blended. Now we can find some interesting points here. First off, the spectrum looks terrible. This was stated, well, this is old. The state of the art of the line data and whatever produces missing features, features that are present but don't exist. Only this feature and this feature match in position and width. The depths of the lines vary. Some are too deep and some are not deep enough. This one is interesting because it's actually 6 lines, 2 iron 1 lines, 2 iron 2 lines, and 2 chromium 2 lines. And you have no way of figuring out from what you see, which is just one feature, which of those would be wrong and have to be corrected. So you have the same problems in the visible. And when you start putting in molecules as well, it gets really bad. I guess I should have gone to the next picture since I blew it up and it's much easier to see, but here's the little case with 6 lines that merge into one. Now you can never determine a wavelength scale from these data. Look at this. This is the center of the feature. There's no line there. You can't determine it unless you can compute the spectrum well. And it's true of everything else. You wouldn't be able to set a wavelength scale from these spectra. Now here's, we go back to the sun. So this is what I consider a high resolution spectrum. It has signal to noise of a few thousand. and a resolving power of a few 100,000. The 1x line here in black is the solar spectrum, and there's no sign of noise in it. However, if you multiply or plot it at 10x, we can start seeing the noise. There's actually some right there. Now, I've computed the spectrum in several different ways. I've computed it, the telluric spectrum in blue here, the solar spectrum in red, the product of the two in magenta, which is down here, and this is one of the best regions I've ever computed in the sun, and normally it looks a lot worse than this. But we see here that there are missing lines in this region. There are missing lines here, here, here. This iron line, which is 0.26 deep, is a pretty good match if this is a missing line. This feature is a cobalt line, one cobalt line with 15 hyperfine components. So all the green are cobalt hyperfine components. It also has a mixture of calcium, chromium. The red ones up there are CN, plus this water line. And we see that it's a good match. So when I look at the spectrum of Sirius I showed you, I get very depressed. When I look at this one, I feel pretty good. So I think there's some hope. Thank you.
Any questions?
Oh, I'm sorry. 201 nanometers.
I also think that the region is not that bad.
Well, this was 9.1 years ago. If I use my current data, and this is not my current data, my new data, this would be old.
It was pretty old data.
Yes.
Because I'm looking for the mixture of your data and the new calculations
Yes.
and new measurements.
That's good.
Enough while we also have the another star with we also have another star with very with a temperature like Sirius and also slightly over metal rich.
Yes.
And but the rotational velocity is only 3.5, so we could see much more lines, and the resolution, the blending is not as severe, and we also think that is quite nice. I mean that for ultraviolet region there is not as many problems as for the red and infrared.
Really?
Yeah. But at least
That's why we're not going to have any more
at least-
spectrographs in the ultraviolet.
At least in the region from 1,700 to 3,000.
Robert, you described microturbulence as probably being varying with the convective velocity. I think in the year 2000, Martin Asplund did some models of granulation in the sun and found that if you model those granules correctly, you can actually dispense entirely with the concept of microturbulence and even macroturbulence in the models. So what I'm wondering is microturbulence just a fudge factor that we can't really describe properly?
No, it's not in the way I'm using it. It's, in olden times, it used to be a fudge factor in the curve of growth, and people would get very large numbers. But these are actual measured widths of lines. So it is the same. It is a physical microturbulence, not a fudge factor microturbulence, and it's consistent with it being convection and having mass motions, I believe, unless you have some other.
Oh, I don't have any specific
Okay.
knowledge on this, no.
Well,
Wait until Wednesday morning.